Hi and welcome back. Let's get started with finishing up these last bits of periodicity. Most important, looking at the formation of transition metal ions or complexes and how we go about identifying those and working out the charge on these. So transition metal complexes, otherwise known as complex ions, the two terms are used interchangeably, come about because of the small size and highly charged nature of transition metal ions. This means that, as we've talked about before, they have a high charge density. That high charge density can attract ions and small polar molecules to form a complex ion where we have ligands bound to the transition metal center. We refer to anything that forms a dative bond to the transition metal, so these are small molecules or ions, as ligands. So these are what bind to the transition metal center, okay, usually the transition metal ion. They can be a number of different things. The ligand must have an electron pair that it can donate to the ion. Okay, so these are going to be negatively charged, or essentially they must have a lone pair. This is because it is a coordinate or dative bond. So both those electrons are coming from the ligand and being donated towards the transition metal ion. The number of ligands that surround the central ion is what we refer to as the coordination number. So when we look at transition metal complexes, what you'll find is they are typically drawn with square brackets around them. The charge is considered to be delocalized over the entire complex once you have that ligand-ion complex formed. This is shown by the square brackets. So in this case, we can see that we have a nickel ion center with 6 ammonia ligands around the outside of it, which has a 2+ charge. This is referred to as the hexaamine nickel 2 ion. Hexa being that it has 6, and then the ammonia is the amine here, and then the ion is the nickel 2+ here. So because each one of these ligands is neutral, the overall charge is maintained as the original charge on the metal ion. So the charge on the ion is delocalized over the entire complex. With the hexaaqua ion 2 ion, we get, this would be an Fe2+ ion that now has 6 neutral water molecules acting as ligands, forming the hexaaqua complex. The 2+ charge of that ion is now said to be distributed across the whole complex, so we put square brackets around it and make it 2+. With complexes, it is not always the same ligand. So as we see here with the tetraamine diaqua copper 2 ion, there are 2 water ligands, 4 ammonia ligands. These arrows that go from the lone pairs with the arrow towards the copper are indicating the coordinate or dative bond that is formed between the ligands and the copper ions. In this case, the copper must be a 2+ ion because each of the ligands is neutrally charged and we have a 2+ complex charge overall. With the cobalt example that we see here, it is a hexaaqua, so 6 waters, cobalt 3 ion, so it is a 3+ complex. That charge originally coming from the cobalt ion, because the ligands, as I said before, are neutral. So transition metals form these complexes because of their high charge density, and the 3d electrons are not as good or as effective at shielding the effect of the charge, okay, as 2s and 2p electrons are. So when we talk about ligands, there are a number of things that form good ligands. A ligand by definition is a molecule or negative ion which contains a non-bonding electron-rich pair which can form a dative bond to the central ion in a transition metal complex. Typical ligands that we see are ammonia, carbon monoxide, chloride anions, cyanide anions, hydroxide anions, and water. All of these have lone pairs that are able to form the coordinate dative bond. Some are neutral, such as our carbon monoxide, our ammonia, water. Some are negatively charged, our chloride, hydroxide, and cyanide ions. These are each given specific names in their ligand form. So amine for ammonia, carbonyl for carbon monoxide, chloro for the chloride, cyano for cyanide, hydroxo, and aqua. So when we see complex formation, the smaller ions form complexes easier. Okay, so we see the smaller ions forming complexes more readily. So Fe2+, cobalt 2+, nickel 2+, copper 2+, are smaller and hence form complexes more readily than the larger titanium 2+ and vanadium 2+ ions. Complexes form most readily in solution with a high concentration of ligands, so we can swap ligands or form ligand complexes by putting these ions into solutions that contain the ligand. By ensuring a high concentration of the ligand, we will ensure complexation occurs. The ligands surround the metal ion and donate the non-bonding electron pair. Then the transition metal ion acts as a Lewis acid and the ligand is acting as a Lewis base. As I said, we'll talk about this later, but a Lewis acid is an electron pair acceptor and a Lewis base is an electron pair donor. So once we form the liganded complexes, we can refer to the coordination number of the complex. The number of ligands that are attached to a metal is referred to the coordination number, and this number is determined by the number of vacant orbitals present in the metal ion, so 3d, 4s, and 4p, which are available to hybridize. The number of ligands attached to the central atom determines the overall shape of the complex ion, and these shapes are the same ones that we've seen for organic structures where we use VSEPR theory. Typical complexes will usually have 4 or 6 coordination numbers. Some have just 2, but these are rarer. As we can see here, if we looked at our hexa-aqua iron 3 complex, this would have a coordination number of 6 because of the 6 water ligands. The FeCN6, so the hexacyano iron 3, okay, you can see here that the charge has changed to 3-. This is because you have 6 lots of -1 from the ligand. This is no longer a neutral ligand. So the ion must have been 3+ to start off with and ends up with 3- overall due to this excess of negative ligand charges. This would also have a coordination number of 6, but the charge on the ion is -3 rather than the +3 we see with the hexa-aqua. With the copper chloride, remembering that chloride each have a -1, with 4 of those, this means we would be at -4. At -2 here, we must have a +2 copper ion in this tetrachloro copper 2 complex that we see here, which would have a coordination number of 4. The copper complex that we see here, the tetraamine copper complex, the ammonia again is neutral, so the charge on the complex is the same as the charge on the copper ion, so this will have a charge of +2, and it has a coordination number of 4. The silver complex we see here, the silver amine complex, this is an example of a coordination number 2. Of course, the ammonia is neutral, so the silver must be +1 as the overall complex has a +1 charge. So when we look at complex ion shapes, we look at the number of ligands that are bound. If we have 2 ligands, and so a coordination number of 2, it will be a linear shape. A coordination number of 4 will be tetrahedral or square planar. And then the 6 ligand coordination number 6 will form an octahedral shape. Silver will generally have only 2 ligands forming a linear complex. Copper 2+ will generally have 6 as its coordination number, and it will be in an octahedral arrangement for copper 2+. Ligands that transfer a substantial negative charge, such as the cyanoligand, produce a reduced coordination number. So you will see 6 ammonias with nickel, but you would only see something like 4 cyanos because of that extra negative charge coming from those negatively charged ligands. So here are some more examples where we see the things that I was just talking about. You'll note the way that we have the complex written with the square brackets and the charge in the top right-hand corner, and the use of the arrow showing the coordinate date of bond. We can see here the nickel 2+ with the larger cyano groups, the Fe2+ with the 6 aqua groups, copper 2+ with the 4 chloro, and then silver with the 2 amino. As I said before, these liganded groups can be the same or different. So we can see here on the cobalt ion that we have the hexaamine, but on the copper here we have a tetraamine diaqua complexation for the ion. We can see isomers with complex ions. This shouldn't come up much for you guys on your exams at this stage. So there are 2 types of isomerism that we see. These are stereoisomers, remembering, so we can have stereoisomers, the mirror images of each other, okay, or ionization isomers. So you can see here that the ionization isomerism, we have complex compounds in which the elements are the same, but the identity of the cation and anion differs. So in this case, we have a single bromine with the 5 ammonias, and in this case, we have swapped that out for an OSO3. So the one that is outside the brackets here, this is the counter ion. Okay, so these will form ionic complexes where you have the charge, in this case, the positively charged complex with the bromine anion. Okay, and here we have the positively charged complex with the sulfate anion. So the counter ion to these complexes is different, so therefore we see a different complex formula with the counter ion. These are isomers. In the case of our platinum complex here, we have cisplatinum and transplatinum. Okay, so the Cl's being on diagonally opposite sides of the platinum ion in this square planar arrangement, or on the same side. As I said, they can show up, but usually you'll be given more information these days rather than having to identify the isomers yourself. So that's it for how we show coordination number, charge, and the molecular structure of our complex ions. Next, we will look at why these complexes are colored and how we go about explaining that.